to the table. This is the problem. All dresses should have pockets, right? Thank you. A principle that people can get behind. Okay, can you hear me? Yes, excellent. Okay, hello everybody. We've had a long day. I don't know about you, but I'm feeling a little tired from all the sun this morning in a happy like post-canoe way. So hopefully I will be engaging enough to keep you focused through the last stretch of this. We're going to be talking about the cosmic microwave background. The two talks, yeah, I don't even know how to point. It's so big. I don't know how to point with this. I'm going to try to use my cursor, which you can see up there, right? Yeah, you can. So the two lectures today are going to be divided into primary and secondary CMB anisotropies. I'm going to give some background, but not all the background you're going to need to understand the cosmic microwave background. So the main goal of these two lectures today are to try to give you a little bit of the tools that you might need if you go into a colloquium and you get a CMB speaker like myself, and you're like, what are they showing here? So if I can give you some background so you can make a little bit more sense of CMB talks, that will be meeting my goal today. So in lecture one, I'm going to give you some quick context for the CMB, talk about primary anisotropies, and then spend some time with the power spectrum, because you're going to see this all of the time from CMB people, and we're going to talk about what kind of physics of our universe we get from the power spectrum and why. And then we're going to dig into the status of polarization and temperature measurements, which are kind of the state of the art when we're looking at primary CMB anisotropies. And then we'll discuss some tensions. That's the hot topic, right? We're all interested in tensions here, and discuss what areas of interest people are studying in the CMB community. And then tomorrow, we're going to go into instrumentation and dig into, okay, cool, I want to study the CMB. How the heck am I supposed to do that? Okay, so when we're looking at the CMB, we're seeing this snapshot of primordial plasma at the time of last scattering, or the epoch of recombination. And you can think of it in terms of temperature and polarization, roughly. Temperature encodes distribution information of these early density fluctuations, gives you positional information of where these things are. And polarization you can think about roughly as encoding the dynamics of this early plasma. This includes things like gravitational waves, which is the big hot topic in B-mode polarization. So these are the primary anisotropies, and then you also have everything in front of the CMB. So you have lensing from gravitational lenses, you have scattering events from hot electrons, you have emission from emissive sources, and all of these things are deemed secondary anisotropies, and that's what we're going to be talking about after our brief bio break today. So the maps of the CMB that we have to work with today are in impressive detail only because of the advancements in technology that we have been able to achieve as humans. In just a short number of decades, we've gone from maps that look like these from the COBE satellite to the high resolution, high sensitivity maps from Planck. And this, again, I'm just plugging how excited I am about instrumentation. We'll talk about what enables these improvements in CMB mapping. And today we'll focus on why we're interested in doing that. Okay, so let's dig into the power spectrum. How many of you have seen these in talks? How many of you feel confident that you understand what this is? Okay, that's good. I saw some wiggling, good. So hopefully I won't bore you too much with what this is. But the essence of this is you're seeing data points from experiments plotted over this line that is a fit to the data points. That line returns to us the parameters of lambda CDM cosmology. It's through these measurements that we've been able to measure these parameters with such exquisite precision already. And we're trying to do a little bit better now in terms of the portions of this plot that I have grayed out. So in talking about the temperature power spectrum, we're encoding the statistical properties of the temperature fluctuations of the CMB. And we do this by using a correlation function. And the power spectrum is a convenient way of expressing this correlation function information. So we expand these temperature signals in terms of spherical harmonics. And you might see L appearing regularly through this talk. L gives you angular scale in the sky. Small l, large angular scales. Large L, small angular scales. And then the expansion coefficients are returned to us by this integral over the temperature and the spherical harmonics. I can't get into the amount of detail I would like to today on this, so I would like to point to you Blake Sherwin's Cosmology School summer slides, where he got into more detail. So if you are interested in the full derivation of these things, please check out that link. So we can write down the angular power spectrum. You see this expression that is defined as an average over every an average over m for every L in terms of the expansion coefficients. And this returns to us our power spectrum. It's customary to scale the y-axis of the power spectrum in different ways that might be convenient to you at different times. One custom is to express the contribution per log interval in L to the total temperature fluctuation and express it in terms of microkelvin squared. But this gives you a summary of the statistics of the temperature fluctuations in the CMB in units of microkelvin squared. Now, it's important to note that for our CMB, we really only have one realization of the CMB. We've already talked about this in the summer school in a variety of ways. If we wanted complete information about the cosmic microwave background, we would need a large ensemble of maps, independent realizations of the CMB. We lack this. We are here in this one reference frame. And so all CMB measurements, even from satellites, the ground, are connected with the uncertainty called cosmic variance. We've talked about this a lot. But you might hear it referred to in papers and in talks as measurements being cosmic variance limited. That means you are approaching this fundamental limit. Your uncertainties are small enough that this is what is limiting your information. And for example, I'm indicating here, that's what happened with the Planck satellite at low L, for example. Okay. Now, I did put this in the Slack. This is a little tool online that you can open and play with. So take a minute and see if you can open this up. We're going to spend a little time talking about how the parameters of our universe change when you change the power spectrum or vice versa. In this tool, there's also the matter power spectrum. We're not really going to be talking about this today. There's a whole wealth of information in here that's really interesting if you're interested in digging in later. It describes the density contrast in the universe. It's the Fourier transform of the matter correlation function. So it kind of gives you the clumpiness. So neglect that from this conversation. But play a little with the sliders, and I'll keep talking, and then I'll have a question for you to answer. So when we're looking at the power spectrum, we're encoding the physics of the early universe that you can think of as a landscape of these potential wells and peaks and troughs with baryonic matter acting kind of like the ball and spring system here, where springs represent pressure, and the system is interacting inside of this gravitational potential well. This is dictated by dark matter. It's kind of indicated by this blue line. And in these gravitational wells, you have a baryon photon plasma that's oscillating and producing sound waves that then propagate through the universe, giving us these baryon acoustic fluctuations that are encoded in the rippliness of this power spectrum. The baryon density that we're looking at corresponds directly to the CMB temperature. And the way I remember this is it's kind of the opposite of what you might think, because areas of high density become cold spots, and areas of low density become warm spots. I can't even say it, it sounds backwards, but that's because photons need to come out of these gravitational potential wells in order to reach us. And so the fluctuations we see are corresponding to hot and cold spots based on, let's see if I can do it, low and high density. There we go. And so you can look at the power spectrum of the CMB and point to different parts of it and roughly say, okay, at low L, we're going to be observing our tensor to scalar ratio. Not here, but in polarization, we'll get to that later. And then we have that first peak of our oscillation, and this corresponds roughly to what you see by eye. So if you look at that Planck map, you are doing a Fourier transform with your eyeballs and saying, I'm noticing that the peak variation here is on degree scales. That's what that first peak shows you. And then from there, you get the compressions and rarefactions from the baryon acoustic oscillations. And then you get photon diffusion, which is saying by photons free streaming, you are kind of washing out some temperature signal because you are averaging out at small scales the temperature fluctuations in this plasma. Okay, so hopefully you've spent a little bit of time with the tool so far, playing with the bars. One thing the tool lacks is varying the curvature parameter. They assume a flat universe. So I put in this little GIF that shows you what would happen to the power spectrum if you were to vary the curvature parameter. Does anybody know why it looks like this? I'll take a drink while somebody takes a guess. Yes. Why would varying the curvature of the universe shift the peaks of the power spectrum in L? Okay. Okay, so you're saying there's something changing about distance scales at recombination because you're changing curvature. Right, and so can you map that to something intuitive about the way we're receiving light from the CMB? I think you basically have it, so I'll finish your sentence. When you change the curvature of the universe, you're changing the way that these, like you said, angular diameter distances appear in the CMB. So they're going to be larger or smaller. That's going to shift the location of the peaks in angular scale. So that's right. Okay, so we're going to move on from that. One other kind of thing to note, I think, about this tool that is a presence in modern CMB analysis of the power spectrum is our relative uncertainty in terms of the optical depth to reionization. So we know that the universe was reionized at redshifts between 6 and 10, and CMB photons are scattered off of this ionized gas, with tau being the optical depth that involves an integration over this time period of the Thomson scattering cross-section and the number or density of electrons. And what this means is anisotropies get attenuated by a factor of e to the minus tau, and we don't have a very good handle on what tau really is. So this is one area where we put priors in place. We give some information to ourselves because we lack a great understanding of what the optical depth to reionization is. You can play around with the tool and see what happens when you change tau. And one thing I wanted to note that is just important for talks is that there is the tau, and then there is tau of astrophysical bodies. And so in secondary anisotropy land, I'm going to talk a lot about optical depth and tau, but that is the optical depth of relatively very small clusters of gas, in which case we introduce some locational information about where we're looking. But this is the tau, meaning all of the gas. Okay, so we've already walked through this. I'm not going to spend too much time here, but basically we are interested in making excellent measurements of the CMB power spectrum and later the polarization power spectrum because you can really glean a rich set of information about the early universe. And we've talked about all of these things briefly. There are other effects too, but they are generally more complicated and kind of beyond the scope of this. So I'm going to ask one question here, then we're going to move on. And that is, I would like you to spend a little bit of time thinking about baryon density's influence on the power spectrum. So play with that slider, give some thought to the system we've just set up, and see if you can come up with a little bit of a laundry list of how baryons are impacting the power spectrum. If you get a good one, just shout it out. Yeah, the height of the first peak. What else? Well, you already win. If I had treats, you'd get one. I don't have any, though. You get the metaphorical treat. Yes, in the back. Yes. Do you know why? Okay. Cool. We'll marinate on it. We'll think about it. Yeah. Right, yep, that's great. So to rephrase, the reason that we see changes between compressions and rarefaction is that there's going to be a change in the relative density of these overdense regions. All right. Cool, so this GIF kind of summarizes it. I think it's actually much easier to see in this GIF than in the tool. So I'm not really sure why exactly that is. I think that might be an indication that the scale really matters in terms of what you are plotting. So yes, the amplitude increases as you increase the baryon density. That makes sense since you're putting more weight kind of into those golden balls of that cartoon with the springs. Every other peak of the power spectrum is enhanced. Remember, these peaks are always positive. So in terms of oscillation, it's up and down, but they're all up here. So it's compression, rarefaction, compression, rarefaction. So those are changed relative to one another because you are changing this density. The oscillations are slowed down, so we're shifting a little bit to higher L. And there are damping changes at high L. I think that's one thing, I guess, that was not mentioned by you all in the first few minutes of this, which was if you increase the baryon density, you are reducing the free path for photons to travel. So you have photons kind of knocking into baryons more often. This means there's less opportunity for that diffusion effect, which means it gets smeared out a little bit. It's less of a steep drop off in the damping tail. Cool. All right, well, you flew through that. So now we're going to change to polarization. I'm not going to go through the details of this either, surprise, surprise, but I will mention that we talk about these things as E modes and B modes. It is tempting to think of this as being a direct application of E and M because of E and B, but it's mainly a metaphor to say that these modes are gradient or curl-like, and that they're derived by the Stokes parameters, Q and U, where E modes have some Q and no U, and B modes have some U but no Q. It's almost like a Dr. Seuss book. And so we can write down what these modes look like and separate them out in terms of maps in the CMB. And we do that. How many of you remember the 2014 BICEP results? Okay, good, some people. This is where I start to feel like my age is increasing, where people are like, what? But this was a very vivid moment in CMB history where B modes were claimed to be measured and it was all foregrounds. So we're gonna be spending a lot of time talking about foregrounds here to kind of beat into everybody the importance of foreground measurements. But to give those people some credit, B modes are incredibly difficult to measure. This is no easy feat. It was already a noble quest, and we continue on that quest. So when we look at the polarization power spectra of E modes and B modes, you see them just being lower amplitude than the temperature measurements, and you'll also see the uncertainties in these plots increasing. That's just because they are harder to measure. They still give us rich information about lambda CDM cosmology, so we're interested in studying them to understand fundamental physics. The shape and the amplitude of the E mode power spectrum, for example, are predicted by lambda CDM. And the physics that we're really after here from gravitational waves predicts the shape of the B mode polarization spectrum. And measuring this amplitude would provide a direct handle on the energy scale of inflation, which would be rad. So these are the kind of lower portions here. B modes aren't present, I'll show them later. This is E modes and then TE. And if you start seeing letter salad in CMB power spectrum measurements, it's because you can take a correlation function not just in that one map, but between two maps, where here now this might be a little hard to see because it's small, but the indices I and J can be different types of maps. You can have T and E, which is shown here. And you can mix and match to your heart's content and look at correlations there, and that gives you more information about various types of estimators you might use to understand the power spectrum. I think that's all I wanted to say. It's harder to measure. The uncertainties are larger. That's basically the takeaway. And now here you can start to see what the B mode polarization would look like. And this is kind of the current landscape of where we are at in terms of measurements here. This is hard work. A new paper just came out from the South Pole Telescope collaboration, mapping out B modes and E modes. And I wanted to spend a moment on this plot and just make a few remarks. One is you'll see just the amplitude here of the temperature signals are smaller. And another is you see some changes at various frequencies. And one more detail that I wanted to ask is, can you note something in the 220 gigahertz data? Make some observation here. Yes. That's true. That's true. I hadn't thought about that. That is true. I don't have any deep insights on that, though. Yes. Yeah, so you're noticing something here? So the authors point out that this is an area of high foreground emission. So you are noticing foregrounds. And apparently the fields that were chosen by experiments that make constraints that have a lower upper bound on R avoid this region of sky. So this is just one indication of why field selection is so critical to making these measurements. The most stringent limits on R are at this 0.036 number from bicep Keck. And we're going to do better with near-term experiments, but the ultimate limit on this is going to come from CMB stage 4, should it ever be funded. And that will give us an uncertainty related to R of 5 × 10⁻⁴, which would really improve things if we were to get down there. Of course, we might not ever measure R, but if we did, it would be fantastic for a wide variety of reasons, and Tom gave us some insight into that on Monday. One of these reasons is just that we have all of this information that would suggest, suggest that we would see inflation. We just don't have the smoking gun. So it would be great to see it. Yes? That's a good question. They are present. I think they're just a little harder to pick up by eye. The authors say that it's mainly that. I did look into what the uncertainties were for, so I'm not involved in SPT, but in other experiments, it's common that the noise is higher with 220 gigahertz data. That is true for this experiment too, but I'm not sure that that directly correlates to us being able to see it more easily by eye in this plot. Okay. It's funny, I have all of this audience engagement in the first half, and then the second half I'm gonna leave you alone largely. So I'll ask you another question, and then you're almost done. Can you name where small versus large L is important for this laundry list? And I'll run through the laundry list. We want to measure the tensor to scalar ratio. We want to better understand the dark sector. Part of that is probing large scale structure. We want to put bounds on neutrino mass, explore light relics. That's that N effective number that we've talked about in the school when talking about neutrinos. We want to look into how galaxies evolve. This is where the secondary anisotropy science becomes really exciting. And then we can use things like transients to turn our millimeter wave surveys into actual astronomy experiments and look at astronomical objects and probe the epoch of reionization. So let's see, what do you think we need to do most of this, I guess, it's a leading question. Tensor to scalar ratio, we need high L or low L? L being multipole moment. Low L, yes. What about the dark sector? Yes, why high? Yeah, that's fair. Yeah, so if we are starting to hone in on dark matter halos, we're going to need high resolution imagery. Yep, exactly. Large scale structure has the word large in it. So, yes. Okay, somebody show their thinking for low. Why low? Okay, and somebody show their thinking for high. Yeah. Yeah, great. I would say it's all important. And just one ironic thing is you can start to get high resolution large scale structure by going to large L. Neutrino mass? Low. High. I'm hearing both. Do you know what the predicted upcoming best constraints on neutrino mass from the CMB is supposed to come from? It's a secondary anisotropy, so we're not there yet. Does anybody know? It's from weak lensing, which you want these high resolution maps for. So maybe both, but definitely you want high resolution. Okay, light relics. Yes, high L. And then the rest I'm just gonna throw into the high L basket because I like large telescopes. Low L is also important in a variety of ways, but less so for astronomical imagery, obviously. Okay, great. We've talked about this. We know polarization. And here, I will just say there are lensing B modes that we need to worry about when we get into secondary anisotropy land. We're going to talk about those a lot so that we can drill down and get to inflationary measurements. This is a lensing mass map. We'll again get to, is it not working?
No, it's good.
It's good, okay, great. Thank you. We'll talk about this lensing mass map. This is what we were talking about, having the high resolution imagery and wide area surveys being important. Oh, I'm so loud now. Oh, okay, thank you. No, it's great, it's great. And then this is just an image of what the sensitivity to N effective looks like in kind of a dramatized way here, where I'm glad I don't actually need to run through this because this has already been introduced, but the effective number of neutrino species would give us some insight to beyond the standard model physics if there were other light relic particles involved. Okay, we're gonna switch gears and talk about tensions. Let's see, I'm 30 minutes in. I think that makes sense. Okay, great. We're doing fine. Okay, who has heard about the Hubble tension? Yes, we've all heard about the Hubble tension. One thing I just love about the Hubble tension is the illustration of why it's important to make better measurements. It's easy to think that if you stay here, you're like, hey, we agree, that's great, let's pack it up. And it's only by decreasing your uncertainties that tensions can start to be revealed. And in a short number of years, this is an indication that there may be new physics someplace or a dramatic re-understanding to be had about the way we are approaching this measurement. And this, in general, is the way that new physics can be dug into. So if anybody asks you, why is it important to reduce your uncertainties on this measurement? Aren't you just satisfied? Maybe you can point to this and say that it is important. And this is just my favorite picture of the local distance ladder. This was roughly my understanding of things until I joined the Duke Cosmology group, where we actually talk about the distance ladder. And it's easy to sit in one camp and point to the other and blame the other for systematics. But there's lots of people working on this right now, and we haven't quite gotten there. So these are some results from ACT. All of the plots I'm going to show from here on out are ACT DR6 plots. This is a fair representation of the field in the sense that CMB measurements are largely self-consistent. We are in agreement with other CMB measurements. In general, when we are looking at these plots, we're constraining parameter space. Here we are showing H0 and the radius of the sound horizon. And we are not seeing consistency with measurements from shoes, for example. There are other data sets you can construct. This is the, what is it, Chicago, Carnegie, Hubble, something with a P. It's a collection of data that is less constraining in terms of high H0 than the shoes results. But depending on who you ask, people will argue for its validity. But in general, we are not seeing agreement here, even with the most recent and most stringent CMB measurements we are making. We are low in the Hubble tension or Hubble constant relative to these late time universe probes. In these plots, you will typically see many combinations of data sets. So here we have ACT data in blue, Planck data in orange, and a combination of Planck and ACT in the purple. In general, by combining data sets, you improve your constraints, and so you will see this parameter space decreasing as you are adding in data. On the right-hand side, you see the matter density and S8. S8 is related to sigma 8. This is a measure of like the clumpiness of the universe. And there is another tension here, but at a lower significance than the Hubble tension. And this plot is showing that when compared to weak lensing measurements, you do see CMB measurements being a bit high. And I did mention that the CMB community has seen consistent results. So SPT just had some recent CMB results, and they found similar things. I just took this slide straight from Colin Hill, who did some great work on looking at the possibility for an alternative non-lambda CDM input of early dark energy. This was motivated to resolve the Hubble tension. Here you can see a diagram of lambda CDM cosmology with respect to shoes and what it would look like if you insert this period of early dark energy and how that moves that parameter space up closer to agreement. How does it work? It works by decreasing the physical size of the sound horizon in the CMB. And as we just showed in this plot, if you move around your value of the sound horizon, you might push yourself into some better limits depending on what you're comparing to. The radius of the sound horizon is dependent or related to the Hubble parameter as shown in this equation. And what you are doing in early dark energy is inserting dark energy parameters of state that differ from what we would have in lambda CDM cosmology. I refer you to Colin's papers if you want to go through the details of this. There was some exciting evidence from ACT data release 4 that gave us like a 3 sigma indication of early dark energy being permitted by the data set. This plot shows you the probability of H0 compared to the tip of the red giant branch sample, which again, kind of looked upon in a certain way by members of the community, and SHOES, and seeing how you can move the parameter space based on early dark energy into better agreement. But this is ruled out with DR6. So this plot shows you the bound on H0 from primordial perturbations, and then where the bounds would be based on various models, where the models are spelled out in this part of the plot. And so early dark energy would be here. It does push H0 up, but not enough to remedy this tension. So if you're interested in the details here, there are very many models that you can work through and do something with much greater detail and rigor than we did playing around with our sliders. But essentially, by moving around the parameters that would go into this, you will change your power spectrum and measure whether or not that could be accurate. And this paper goes into the detail of doing that. Another thing we were interested in studying is neutrino mass and neutrino mass ordering. So the normal ordering expressed as NO here, an inverted hierarchy as IO, inverted ordering. And we are seeing still consistency with there being 3 neutrinos. We're not seeing evidence for new relativistic species yet. And again, when we take leaps into the future with CMB experiments, we are going to be improving our uncertainties, which means we open the window for there to be some differences that we're not yet seeing. But right now, we are consistent with Big Bang nucleosynthesis. This plot shows you the parameter space constrained by our most stringent data set, Planck and ACT. In neutrino mass, this is the sum of the neutrino masses and the matter density. And I think this plot is a little bit, I don't know, there's something about excluding the normal ordering at 87%, but it's essentially saying it's favored over inverted ordering. So I think we are at the second part of this, and maybe we have a few minutes for a couple questions before our brief break, and then we go into secondary anisotropies. Yes?
So that's why I thought recent people propose that removing low L can give you higher optical depth and also, neutrino mass that is other. I thought, am I wrong or?
I think there is a lot of content in that question. So I think let me start with, I think you asked whether information about neutrino mass is present at high L. My understanding is that it is true that high resolution images can be used, or sorry, high resolution CMB maps can be used to make power spectrum measurements that are relevant for the constraints for neutrino mass. So I don't think it's true that there's only a specific bound in L that is useful for neutrino mass constraints. And then the other part of it was something about reionization and optical depth. So I think this might be getting at the level of uncertainty we have with respect to optical depth. And it's true that getting a better handle on tau is going to give us improved sensitivity to things like neutrino mass. There are degeneracies here, which is really motivating more information about the optical depth of reionization. And I think what you're saying about measurements at low L being important for that may well be true. So I think that is right. But it's not saying that high L measurements for neutrino mass aren't important.
I don't know that's better, and then I thought that's why the ground-based ones will not improve on the optical depth on the system.
Yeah, so I am not making claims on which part of the power spectrum are best to measure optical depths. And I also, that's a good question. I am not sure what is positioned to make the best optical depth measurement in the near future. It might be that a space-based experiment would do better with that. Good question, though. Lots of thinking there. Thank you. Any other questions? Yes, thank you.
Thank you for the talk. So we traditionally want to look for the, I guess, primordial B mode signal at low L, right, where the lensed E mode signal is lesser relative to the B mode signal. And so I just was wondering what sorts of degeneracies exist between the reionization bump that we see at those low L and, you know, potential peaks in our primordial B mode signal.
Yeah, great question. I think the name of the game is going to be improving sensitivity across the board so that we can eke out differences between the two. If your measurements are up here, you will not be able to resolve those. So it's only by improving your noise floor and improving the depth of these maps that we'll be able to push down in there, in addition to controlling for systematics. So you'll see a whole bunch of plots about this coming up, where foregrounds have some certain behavior, lensing B modes have this other behavior, and it's only through handling of systematics that we'll be able to dig down between the two. In terms of the theory that goes into defining those two, I don't have any further intuition other than what's shown in this plot, meaning if they have different values, they might be harder or easier to separate based on the shape of that power spectrum. Yes.
Does your lensing B mode curve have a neutrino mass assumption on it? Is that what that says?
I'm sorry, there's a little feedback. Does the
Like your green curve, does that have a
green
something
curve,
saying your neutrino mass is
does it have something to do with neutrino masses?
like it looks like on your
Yeah,
purple?
so this is just having the sum of the neutrino masses being between, it's really hard to read, 0 and 0.1 EV
Oh, okay,
for
okay.
the definition of what's
Yeah.
being plotted. Yeah,
Okay.
thanks. It's a good eye exam test. Okay. I think we could do bio break and come back and do secondary next.